Hello students, here's a curious question to start us off. Why don't electrons ever get tired running through circuits? Because they're always charged up. Now, let's talk about how resistors can team up inside a circuit. Resistors don't work alone, they combine mostly in two ways, either in series or in parallel, and this changes how the total resistance behaves. When resistors are lined up in a series, the current flowing through each resistor is exactly the same, like runners passing one baton along a single track. But the voltage across the circuit splits among the resistors, each taking a share depending on its size. On the flip side, in a parallel combination, every resistor experiences the same voltage, kind of like runners standing side by side in their own lanes, each seeing the exact same starting gun blast. However, the current divides inversely with resistance, so the smaller resistor hogs more current. Understanding these differences is key because the total resistance changes with each arrangement, and this affects how we apply Ohm's law to calculate current and voltage in the circuits we design or analyze. Imagine three resistors named R1, R2, and R3 connected in a series line, one after the other, like cars parked bumper to bumper. In this setup, the total resistance of the entire chain, which we call the equivalent resistance, equals the sum of the individual resistances. Let me show you how that works with Ohm's law. Remember, Ohm's law says voltage V equals current I times resistance R. Since the current is the same through all three resistors, the total voltage across them is the sum of the voltages across each resistor individually. That is, total voltage V equals current I times R1 plus current I times R2 plus current I times R3. We can factor the current I out, making this V equals I times the sum of R1 plus R2 plus R3. And that sum inside the parentheses is what we call the equivalent resistance for resistors in series. This means the more resistors you add in series, the higher the total resistance, which makes it harder for current to flow. The circuit gets a bit like a traffic jam on a narrow road. Now, let's switch gears and look at resistors connected in parallel. Picture three resistors placed on branches side by side, like multiple lanes on a highway. Each resistor in this parallel setup experiences the same voltage, just like each lane sees the same traffic signal. But the currents through each resistor, named I1, I2, and I3, differ depending on their resistances. Applying Ohm's law to each, current I1 equals voltage V divided by resistance R1, current I2 equals voltage V divided by R2, and current I3 equals voltage V divided by R3. The total current I flowing into the entire parallel system is the sum of these branch currents, I equals I1 plus I2 plus I3. Substituting the current values, total current I equals voltage V times the sum of 1 over R1 plus 1 over R2 plus 1 over R3. Rearranging, this means I equals voltage V divided by equivalent resistance R1, which leads us to the important formula, 1 divided by R1 equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. This shows that the equivalent resistance in a parallel combination is always less than any individual resistor's resistance, since the paths multiply the ways current can flow, much like adding more lanes reduces traffic congestion and allows more cars to pass. Let's compare series and parallel arrangements side by side to highlight their distinct behaviors. In a series connection, the equivalent resistance is simply the sum of the resistor values, R1 equals R1 plus R2 plus so on, which we've seen increases total resistance and reduces current flow. In the parallel connection, the equivalent resistance formula is the reciprocal of the sum of reciprocals, 1 divided by R1 equals 1 divided by R1 plus 1 divided by R2, and this continues for all resistors. Series circuits maintain the same current throughout the whole chain, while parallel circuits maintain the same voltage across each branch. Another important difference: if a resistor fails in a series, the entire circuit is broken like a broken string of Christmas lights, but in parallel, the other branches keep working, just like a power strip where one socket fails but others still supply power. Power dissipation also behaves differently. Power equals current squared times resistance, so in series circuits, increasing total resistance affects power loss differently compared to parallel circuits, where higher currents and branches change power distribution. Let's bring these formulas to life with numbers. Consider three resistors with resistances 2 ohms, 3 ohms, and 6 ohms. First, in series, we add them straight up. 2 plus 3 plus 6 equals 11 ohms, which is our equivalent resistance. That means the resistor chain acts like one big resistor of 11 ohms. For the parallel case, we use the reciprocal sum rule. 1 over R8 equals 1 over 2 plus 1 over 3 plus 1 over 6. Adding these fractions, 1/2 plus 1/3 plus 1/6 equals 1. That simplifies beautifully, so the equivalent resistance is 1 ohm. This example highlights how the arrangement drastically influences total resistance, showing how series increases resistance and reduces current, while parallel reduces resistance and allows more current to flow. The accompanying diagram shows both series and parallel connections side by side, each clearly labeled with resistors R1, R2, R3, current I, and voltage V, giving you a solid visual to match these calculations. Sometimes circuits get tricky, mixing series and parallel connections in one system. Imagine some resistors connected in series and others in parallel, like lanes on a highway that merge and split again. To find the overall resistance, we simplify step by step. First, identify the inner groups in series or parallel and replace them with their equivalent resistance. For example, if R1 and R2 are connected in series, we add them up to get Rs. Then, if R3 is in parallel with this series group, we apply the parallel formula 1 divided by R8 equals 1 divided by Rs plus 1 divided by R3. This stepwise approach helps simplify complex networks, which are common in everyday household wiring or gadgets, preventing confusion and ensuring correct analysis. Power usage depends heavily on how resistors are connected. The power consumed by any resistor equals current squared times resistance, which means changes in total resistance in series or parallel setups affect the power consumed. In a series circuit, total power equals current squared multiplied by equivalent resistance. Since series connection increases resistance, it typically lowers current but may increase power dissipated as heat in the resistors. In parallel, the equivalent resistance drops, so the total current increases, causing more total power usage. For individual resistors, power can be expressed using current. Power equals individual current squared times individual resistance, or using voltage, power equals voltage squared divided by resistance. This explains why devices in your home designed as parallel connections need careful design to handle different currents and power safely. To recap our journey, for resistors connected in series, the equivalent resistance is the straightforward sum of all resistors. For parallel connections, the reciprocal of equivalent resistance equals the sum of reciprocals of individual resistances. Remember Ohm's law and power formulas: voltage equals current times resistance and power equals current squared times resistance, which can also be written as voltage squared divided by resistance. In series circuits, current remains constant while voltage divides among resistors. In parallel circuits, voltage stays the same and current divides inversely with resistance. This means total resistance in series is always greater than any single resistor, whereas in parallel it is less. Understanding these principles helps us design circuits efficiently, from simple devices to complex electronics, ensuring the right current flows safely and effectively. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.